Hi, in this video I want to show you how to import a robot model you made in Onshape to IsaacLab and IsaacSim and how to train it. Now, the reason why I'm making this video is, although IsaacSim has import from Onshape feature, if you do use it, you'll run into some issues. I'll try to show it to you again. So when the robot moves around, there you go. There are these weird jumps. Please ignore the warning. Yeah. So it has some problems if you try to use it, and the reason is, if you look at the wireframe, the imported model has these sharp edges on the wheel, and IsaacLab really dislikes, or IsaacSim really dislikes these edges, and it causes the physics engine to behave a little bit erratic. So to deal with this, I have a different approach, which is to import the model from a URDF file, and I switch the wheels into cylinders for the collision mesh. And in this video I want to show you how that's done. So here is my robot that I made in Onshape, and it's just parts that are joined together by either the revolute mate or fasten mate. So for example, if the base plate, the top plate and the walls, they don't move, so they are joined using fastened mate, and this wheel and the motor's axle is mated together using revolute mate, which is right here, and the motor, which is the parent, is on top, and the rim, which is the wheel assembly here, is the child. And that's it. And for each you can build your robot from either assemblies, or you can bring in parts directly. So if you have a part, so for example, if I have the motor part, then I can import it in directly, or if I have an assembly, which I have as the caster, then I can bring it in directly like this as well. Okay, so that's the robot, and I have to import the robot, I am going to use this Onshape to robot repository on GitHub, and the installation instruction is, if you follow the documentation, you have the installation instructions here and workflow here, and it's very simple to install. Basically, on Ubuntu you have to just install it through pip and then set up some keys, which you can get from Onshape. Okay, and so let's take a look at how to import this. So in the empty folder, I have to create a file called config.json, and in here I have to put in my the URL of the full robot here. So just copy this and put it in your config file, and that's it. And then you get Onshape to robot and then config file, and you are ready to go. So now it's exporting the robot model to URDF file. Okay, so that's done, and if I look at the code here, I have my URD file here. So what I like to do is I like to use a extension called URDF. Is it this one? Yeah, visualizer here. Just click install here. And what this does is, once you click on the URDF, it creates a little button here, and when you click it, it's supposed to show the robot model. So currently I can't do it because all of my well, the linked assets have this package in front of this, and this is because of ROS. So we're not using ROS in this example, so I'm just going to put package here and then basically just replace everything here. Okay. And so now I have my robot model shown here. Okay, before we move on, I forgot to mention, when you use Onshape to robot, you have to rename all of your mates using either DOF or fixed. So for example, if the wheels are rotating, then you have to put this DOF prefix in front of it, and if they are fixed, not moving, then you have to put fixed in front of it. And I think this is a requirement from using this GitHub package. So another thing that's important is you have to add material to your Onshape objects parts. So for example, I think the tire, I've given it as, well, this is rubber, and on the rim let's see, what kind of material did I assign to this one? Oh, PLA. Okay, so it has a material library itself, so if you start typing, then it can give you the common material and its densities. I don't know where PLA has disappeared to, but PLA is included. And this provides the density, and it also calculates additional properties. So for example, the moment of inertia is calculated for each object after you have decided the material property. Now I'm going to modify my URDF file so I can import it to onto IsaacLab and IsaacSim. So the first problem maybe you haven't noticed is that the x-axis is in this direction, but in IsaacSim, x-axis is the forward direction of the robot. So technically you can still use this, but if you want to use IsaacLab's inbuilt functions, then it assumes x is forward, and you're going to have a much easier time if you have the x basically point forward. So to do that, the easy fix is to define an extra link to just define the orientation of the robot. So I have a file here that's already fixed this. So basically I'm creating something called a base link, and it's called world to base. The parent is, the new base link, and then the child is base, which is the original base name of this robot. And I'm simply adding a rotation here. So if I save it now, the forward x is now fixed, and the base link name is now simply called base link. Okay, so to fix the rotation issue for IsaacSim, I'm going to replace the wheels collision mesh with cylinders. Because if we use the mesh itself, then it has a lot of sharp corners, and we saw what happens if we have sharp corners. So to fix this, I'm going to start with the small wheel here. So the small wheel currently has, looks like here, and I can simply replace that with a cylinder, which is cylinder radius and length properly defined. And for the big wheels, I can also do the same. So let me just copy the. There we go. So let me just compare it. So before it was like this. After I put in the cylinder, it looks like this. And I'm going to do the same with the other tire. There we go. So now we have a bunch of extra collisions that I actually don't need, so I can just remove them. So for example, we have a motor mesh, collision mesh that's inside there. We can just delete this, and this is the left and right motor, and you can see they disappear. The top plate we can leave. This is kind of an object inside the plate, so we don't need this. The walls, the rims I don't actually need because it's fully covered by the cylinder, and this is the cylinder here, and this is the other rim, and this is the caster base. So everything removed. Now our URDF file is much more simplified. The collision, well, this is only modifying the collision, but the base visuals still remain the same. Before we move on, I can now import the robot or the URDF file to IsaacSim, but if you do that, you'll notice all of the colors will disappear. And the reason is IsaacLab doesn't like reading the material color directly. And to fix it, you have to define a material, give it a name, and give it a color. And for all the parts that needed separate color, you have to assign that color to that part itself. So for example, if I have top plate, I'm going to remove this, and I'm going to give it the plate material here. And there we go. And so now it's using this color, and when you import it to IsaacSim, it will maintain this color. Okay, so now we're back in IsaacSim, and we can import our URDF file. This is a movable robot, so set movable base to value. This will set the stiffness and damping value, but I'm going to set these manually, so it doesn't really matter which one you choose here. Collision from visuals, you don't need this because I've already set the visual collisions for all parts of the robot. And allow self-collision, you can either enable or disable this. And we have replaced cylinders with capsules. This isn't really necessary in this robot, so I'll leave it empty like this. Okay, so here is our imported robot, and as before, I'm going to click the ground plane. Okay, and let's set this robot up a little bit. So the robot now has our visuals, and our joints are combined in here, so we need to change a few variables here. So this already has the drive enabled. All of these have no upper and lower limits, so I have to make sure these are on set joints, because if they're 0 and 0, that means this is kind of fixed and cannot rotate anymore. With that done, the caster wheel and base have no damping and stiffness values because these are not driven joints. I guess we can turn this off as well. And for the left and right wheel, I'm just going to set the I'm going to set stiffness to 0. Remember, stiffness is kind of a restorative force, so we don't really want to restore anything in this case. And it has some default damping value, so let's see what that looks like. So back to robotics and differential controller, and we can add our robot again. Radius 4 and 5. This is now called right wheel. Okay, so now if I turn it on, there we go. So before we had some jumping around and being very difficult to work with, but now as you can see, it's very clean and very smooth. There you go. Okay, so let's move on to the training part here, and the training is based on the code provided in the walkthrough on the IsaacLab page, and if you go through these steps, then you will already know how to train the wheeled robot, and I think the code is also in one of the examples in IsaacLab's source code. So I'm not going to go through the details of the source code, but just say where to include our new robot so we can train it. So in our environment config file, I'm going to add my robot's articulation config directly, and I'm going to link it to the file that was I forgot to mention, but you need to save your once we load the URDF, you need to save that file as a USD file. Make sure you don't include the ground plane, just the bot itself, and then just give it any name you want, and then it will provide you the USD file. And then we have to give the simulation the names of the joints that we want to articulate. In this case, we have left and right wheel, which are also provided here. Now, technically, we have a damping and stiffness values defined here, but because the USD is not instanceable, I think that means you can't overwrite it from code itself. So let's set these as none, and then it will read the damping and stiffness value from the USD itself. Other than that, I changed the reward function from the tutorial. In the tutorial, you have a reward term for moving forward, and the second term for making sure that the forward direction of the robot is aligned with the direction that we tell it to go. But these are two separate rewards, so I don't really know why they've decided to multiply these two rewards. Usually you would put a weight value in front of reward functions, and then you just sum them up, which I'm going to do now. So the change I'm going to do is I'm going to add the two different reward terms, and that's it. So let's take a look at what a training looks like. So I've started training with 256 environments. Okay, so here we go. Our robots are now spawned in. The red arrows represent the direction that the robot should go, and the blue arrows represent where the current facing direction of the robots are. So immediately the robots learned how to turn itself to align towards the direction that we want it to go, and it's slowly learning how to also move in that direction as well. And actually within about 30 seconds of training, you can already see it's learned how to rotate and move in the direction that we want. Yep, so that didn't take very long, and if you just let it train a little bit longer, then it will get a little bit better at its moving towards target direction. Okay, so that's it for this video. I hope you found it useful. In the next video, I'm going to show how to train a legged robot with manager-based reinforcement learning workflow. Okay, thank you.